Thank you for the introduction. So this talk focuses on quantitative lung ultrasound, but let's start first from the state of the art. So what can be done clinically today with clinically available scanners? And that is essentially limited to pattern recognition. So what you can do nowadays is recognize the presence of specific patterns in lung ultrasound images. And these images show the most important patterns, such as pleural line, the horizontal artifacts, vertical artifacts, and consolidations. And we can therefore perform this pattern recognition task by a clinician looking at the data, or we can automate it and have algorithms that do perform this task. However, even though we can connect a certain pattern to a number and therefore assign a score based on the presence of these patterns, this will still be at best a semi-quantitative approach because this conversion is surely useful to its communication, but it's definitely not quantitative because it still remains subjective. So these patterns that are often artifacts are moreover not specific, and their presence and appearance strongly depend on machine settings, probe used. Moreover, the intra-operator agreement is generally low in the identification of these patterns and therefore also in the assignment of the scores. And this means that also automated systems trained on the ground truth generated by clinicians will still contain this strong level of subjectivity. Nevertheless, these techniques, although they have these limitations, are still useful to assess lung aeration because you can monitor lung deaeration and reaeration, although standardization is key. And with the standardization, what I mean is standardize the imaging test settings. So you see here, for example, a standard acquisition protocol we developed for COVID-19. Also standardize the areas where you want to scan, meaning how many scans do you want to take and in which part of the thorax. Standardized also the connection between the imaging patterns and the score. And again, this remains subjective and qualitative to a certain extent, but is still useful clinically. In fact, here, for example, for COVID-19, we showed that if you use the standardized imaging acquisition and scoring system, and later on, you're going to add all the scores for every area, you have a cumulative score that can be used for patient stratification. There is therefore a prognostic value, meaning in this case that patients with a score higher than 24 will have a higher risk of worsening than those with a lower score. If you have such a standardized imaging acquisition protocol and analysis system, you can also automate it. So you see, for example, here an example of an algorithm we developed that is going to be to score automatically every frame in a video, also reporting with semantic segmentation, meaning there is an explanation performed by the algorithm that is going to highlight the most important part of the image that was needed for the algorithm assessment. And we can also color code it. So we can code the score into colors to make it intuitive. In this case, for example, you see red is score 3, orange is score 2, green is score 1, and blue is score 0. Then since we want to automate the full process, you don't have to stop at assessing every frame, but you also have to automate the video level assessment as well as the final exam level assessment. And this is what we have done, indeed, during the COVID-19 pandemic. Here you see, for example, a study where we compared the level of agreement in the clinical call, so in the patient stratification task, that we reached comparing on a large clinical study with 100 patients and involving 3 hospitals, where we compared the call of the algorithm with the call of the expert clinician. And you see that they were in agreement in 82% of cases, meaning that these systems are useful as a support tool for clinicians, but they will be failing, in this case, in 80% of cases. And so, on the other hand, it means that these systems can remove the load of the analysis in 82% of cases and limit to 80% of cases the workload to the clinicians. And that's why explainability is important, because the clinician has to see why a certain call has been made. And when the clinician realizes the call is wrong, he or she has to overwrite the code. This system was also deployed in a commercial system produced by Esaote in Italy. Okay, so this is the state of the art. And now towards reimagining lung ultrasound, because of course, as we discussed, we have a problem with current ultrasound technology for the lung, because that technology is not developed for the lung, right? For an aerated tissue, but rather for soft tissue. And therefore, that limits the lung ultrasound to semi-quantitative methods with reduced specificity and reproducibility. While the aim, we should be aiming at, is to understand lung ultrasound interaction with pulmonary tissue, and therefore use this understanding to develop quantitative approaches, truly quantitative approaches, with higher specificity and reproducibility. So what we know is that lung permeability to ultrasound is modulated by changes in aeration, right? And so that means changes in airspace's dimension, spatial distribution, and in variations in the surrounding material, so the material around these air pockets. Now, following the acoustic trap theory, we can hypothesize that we can indirectly derive sort of an acoustic lung surface histology by means of ultrasound spectroscopy. And so to test this idea, we need a model. And so we started creating lung models with controlled bubbles, micrometric bubbles. So we generated, for example, in this case, different population of bubbles with sizes in the range of diseased alveoli. So in this case, we have, you see, bubbles of 170 micron, in this case of 80. We trapped it in tissue mimicking material, creating a sort of a cloud, like a small part of the lung. And so what we checked with this is that if we use not a standard broadband pulse, but a multi-frequency approach where we are sonifying specific frequencies and generating parallel different images at different frequencies, we check these phantoms. And you see here, for example, with standard ultrasound, you're not capable to see vertical artifacts. You only see horizontal artifacts in the phantom with the large bubbles. While when you switch to multi-frequency approach, you start to see vertical artifacts appearing. And moreover, you see them appearing at 4 megahertz. When you move to the phantoms made with the smaller bubbles, you start to see vertical artifacts also with standard ultrasound. But then when you switch to the multi-frequency approach, you see these patterns appear at higher frequencies. And that's very interesting, because when you test with the larger group of phantoms, you see that you can differentiate between the phantom types, and therefore you can differentiate bubble sizes by mean of the native frequency, which is the frequency at which we are receiving the strongest intensity connection to the vertical artifacts. Now, what we think this is actually relating to is not the size of the bubble itself, but the size of the spacing between the bubbles. So large bubbles, large spacing, low frequencies, small bubbles, small spacing, high frequencies. Well, that's very interesting. Then the other thing is that in general, the lung is composed of very diverse bubble areas, right? Because the alveoli are very different. So we would like to simulate something like this with very diverse bubble sizes. And then we did. So we repeated this study, but we used a polydispersed bubble population, and for comparison, also a monodispersed. Now, these two are microscopic images of these bubbles. You can see them as a sort of histology of the lung we are mimicking. And so when we looked at this and we utilized the multi-frequency approach, and this time we don't extract the native frequency, but we extract the bandwidth. That is a parameter that looks at the intensity of these vertical artifacts and how that changes over frequency. Then you see that we found out that the bandwidth do correlate with the variability of these acoustic trap size. So if it's more heterogeneous, we have a larger bandwidth. While if it's more homogeneous, we have a narrower bandwidth. Well, that's very interesting. And then we did recently another study where we generated phantoms mimicking septa in this case. And this enabled us to study whether total intensity would change as a function of the material filling the septa. And indeed, we found out that we can distinguish, for example, between water, milk, and oil that have changes in absorption comparable, for example, to those that you will see going from water to blood and then scar tissue. So we can distinguish also these type of things with another parameter that is the maximum total intensity. So that's very interesting. And then we moved into a clinical validation where we wanted to see whether we could use the multi-frequency approach. We tested on convex and linear probe, whether we could use this approach and these three features to distinguish between pathologies. So we tested this multi-frequency approach with the linear and the convex probe. From here, you see we segmented the vertical artifact, we computed this total intensity and extracted these three features that I discussed before. And so you can plot, therefore, then every patient with respect to these two features, as well as study the variation of the total intensity. And if you use these three features, feeding them to standard classifiers, you could see that we can get accuracies up to 80% in the differential diagnosis between pathologies such as CPE, pneumonia, and pulmonary fibrosis. And this was a study involving 2 centers and 66 patients. So this still had the component where we had to segment manually the artifacts. So that's why we moved to a fully automated analysis now recently. So we're still using this multi-frequency approach, linear probes, frequencies from 3 to 6 megahertz. But now we're going to segment following the pleural line, and we segment a pre-pleura, pleura, and a post-pleura area. We're going then to study the very same parameters I showed you before. And then you see that if you do this, and this is even a larger study with 86 patients involving also COPD as a disease, we can still maintain accuracies, in this case even higher, up to 87% in the differential diagnosis of these pathologies. We then moved beyond static features, we moved to dynamic features. So here what we are doing is quantitatively assess sliding velocity, and we checked whether we could use this to differentiate between pathologies. We used the same patient population as the previous study, so 86 patients. And you see here that we can get accuracies up to slightly above 90% in the differential diagnosis of these pathologies. Further, we are also now investigating the possibility to extract dynamic features, but in a 3D ultrasound acquisition mode. Here we did for now just a simple test on healthy volunteers that are changing their breathing, and we could see how we can assess variations in breathing. And we plan to move forward with this on clinical studies. And then another thing we are recently looking into is to see whether we can further improve the level of control and the position of the probe, because that would potentially further reduce biases due to the fact that the probe is generally handheld by an operator. And in this case, we use a robotic arm to control the position, the probe, and we develop an algorithm to automatically find the optimal position and test it in vitro. So with this, I'd like to conclude by saying that lung ultrasound is an extraordinarily open field to new discoveries and applications. That for sure, lung ultrasound requires standardized acquisition modes and analysis, both for the use with clinical scanners as well as with these newly developed techniques. Artificial intelligence can support in standardizing the acquisition and the analysis. But the future to me lays in the development and deployment of dedicated quantitative technologies that, as shown already by quantitative lung ultrasound spectroscopy, can improve specificity and therefore really allow, for example, diagnosis potentials for lung ultrasound. With this, I'd like also to share with you that the third International Lung Ultrasound Symposium will be held in Trento from 28 to 30 of June 2027. And in this symposium, we have clinicians, physicists, and engineers coming together to discuss the latest developments in lung ultrasound. I also want to thank my lab members and the clinical collaborators, as well as the funding bodies. And I'd like also to thank you for your attention.